Thank you. It's a treat to be here in Riga, and I hope you enjoy what I have to say. I want to thank Wolf Harder for helping sponsor this event. Here's my title. Is Dijkstra's shortest path algorithm optimal? I'm an old guy. I could be retired. Why am I still doing this? Because the field is beautiful, and it's young, and it's still full of possibilities. So I say to all of you who are students, even though you might think that we understand everything, computer science is still a young field, and there's plenty to do, and I hope I can illustrate that with what I have to say. So let me start with some simple observations. Computer science has been around for maybe 60 years, World War II, maybe even since the 30s when people like Turing and some logicians were dealing with the concept of what does it mean, what is computation? How do you define computation in a theoretical way? I'm a theoretician, but I design algorithms, so it's more nitty-gritty. We've been working on this for a long time, but not that long. Plenty of open problems. Sometimes we've settled for the first good enough solution. Sometimes my colleagues like theoretical complication, which is maybe not best. Maybe we should be striving more for simplicity. It's important to note that computers are getting faster and faster and memories are getting larger and larger. This means there's more and more space in which to design efficient algorithms. So my goal, as it has evolved over time, is fundamentally simplicity. The goal is to identify the simplest possible efficient methods to solve basic problems. Paul Erdos, who was a famous mathematician and quite a wit, had many interesting ideas. One of them is this idea of proofs from the book, the best possible proof of a mathematical theorem. This is the book in the sky. We can think about algorithms in the same way. What is the best possible algorithm? We want algorithms that are as simple as possible with provable resource bounds for important input classes that are efficient in practice. And one important component of this is the role of data structures in algorithm design. The key to solving many combinatorial, non-combinatorial problems is to represent the information in the problem so that you can do certain kinds of queries, look up certain kinds of information, and update the information in certain ways. And if you can make those operations efficient, then you get an efficient solution to your problem. So the key component often to get an efficient algorithm is to design or choose the correct data structure. And in the Dijkstra shortest path algorithm, we'll see an example of that. So what is this problem? We're given a graph, which is just a collection of vertices, nodes, and paths between them, arcs or edges between them. And the edges have costs or lengths or something like that. We're interested for certain pairs of vertices in finding shortest paths of minimum length or minimum cost between certain pairs of vertices. The particular version of this problem I'll talk about is the single source problem, in which we're given one starting point, and we're trying to find the shortest path from the starting point to all reachable places. So by shortest, I mean the minimum sum of the arc lengths. I'll denote the length of an arc, VW. This is an arc from V to W by C of VW, the cost. Now, this problem comes up all over the place, notably in route planning. Your phone has various mapping services on it. You ask it to give you a route from here to there, and it will give you at least one, if not more than one possibility. These devices now can do these shortest path computations optimally in fractions of a second. There are special characteristics of the kind of graphs that we're dealing with in route planning, travel time, and so on. They're more or less planar, which means that there are no edge crossings if you ignore tunnels and bridges and things like that. But there's a more important property. They have a certain hierarchical structure, from superhighways down to cow paths. And you can exploit that structure in solving route planning, shortest path problems in practice. And again, the maps that people deal with are very large, and it's too much time to spend on a single route planning problem to look at the entire map. So these algorithms that do this on your phone, notably, this algorithm only works if the edge costs are non-negative, which certainly makes sense in the driving distance problem or the route planning problem, but there are contexts in which negative cost edges are important, and we need different techniques to deal with those sorts of problems. So the goal here is to compute the length of the shortest path from S to every other vertex, or maybe just from S to some vertex. And the way the algorithm works is it employs a greedy strategy, which is kind of obvious maybe when you think about it, but we start out at S, we look at the nearest place we can get to from S, which happens to be A in this case, and we work outward, always trying to find the next nearest point. So let me be a bit more formal about this. We're going to maintain for each vertex a current length, which is the length of the shortest path that we've found so far to that vertex. So for our initial vertex, the distance is 0. We don't have to go anywhere. We're already there. For every other vertex, we'll set its tentative distance at smaller and smaller distances until for each vertex we have the smallest distance, and then we're done. Initially, S is the only labeled vertex. We know its distance, and all the other vertices are unlabeled. So here is the entire algorithm. It's a simple, greedy loop. We've got this labeled set, initially just the source vertex. We delete from this labeled set some vertex that has minimum tentative distance D of V. And then we're guaranteed, this is the theorem we have to prove, that this value is in fact the correct shortest distance for this vertex V. And then we see where we can get to from V by one step and do an appropriate update. So I'll call this updating from vertex V the scan of V. We look at all the outgoing arcs from V to W. If W traversing the edge VW, we'll do the appropriate update. If the current value is D of W, if the distance to V plus the cost of the arc VW is less, we'll just update the value. And this is the entire algorithm. After we've done the updates for vertex V, this possibly changes the labeled set. We pick the next vertex out of the set that has minimum distance, and we continue until the labeled set is empty, at which point we will have visited all reachable vertices from the start vertex and computed the correct lengths of shortest paths to all of them. Going back to this example, we start out with just S in the labeled set. To scan S, we've got an arc to A that gives us a tentative distance to A of 5. A was not visited before, so it goes in the labeled set. To C, we have a tentative distance of 6. It goes in the labeled set. And then we're done with S. And you will have seen this algorithm if you've taken an elementary data structures or algorithms course before. I just want to set the stage for what I'm going to say about it. So now we've got 2 vertices in our labeled set, but A has the smaller tentative distance. We remove A from the labeled set, and we're now guaranteed by the properties of the algorithm, essentially the non-negativity of the arc lengths, that we have the correct shortest path to A. And now we scan A, which means we look at its outgoing arcs, to B, which gives us a cost to B of 19 and puts B in the labeled set, and to D, which gives us a cost of 14 and puts D in the labeled set. So now we have C, D, and B in the labeled set. And now maybe we'll do one more step here because now something different happens. We have C, D, and B in the labeled set. C has the smallest distance. Now we scan C. We put F in at cost 10, but also we've got a better path to D now because we've got 6 to C, and that's optimum, plus another 6, which is 12, which is less than 14. So D is already in the labeled set, but its value decreases because we found a better path. So we change this value to 12. And next would be F. You will notice these vertices are not scanned in the order in which they were inserted into this labeled set L. They're scanned in order by distance, shortest to longest. But that's the entire algorithm. And I won't go through the rest of it. The critical point is that when a vertex is scanned, when it's minimum in the labeled set, it's guaranteed that the distance is correct. And that essentially comes from the non-negativity of all the arc lengths. Another important property that follows from the fact that you're always picking the minimum is that you're pulling the vertices out in non-decreasing order by distance from S. There can be ties. So Dijkstra's algorithm actually does more than compute shortest distances to all the vertices. It identifies the order of the distance order of the vertices. That is, it pulls the vertices in order shortest to longest in terms of their distance from S. I'll call this the distance order problem. And you can also augment it to maintain shortest paths as well as lengths of shortest paths. One can build a so-called shortest path tree that represents a shortest path to every vertex that's reachable from S. And essentially all you have to do is keep track of the arcs that define the most recently computed distances, and this will give you all the shortest paths. So it has some very nice properties, but I want to focus in particular on this distance order problem. This algorithm is doing more than we stated in the original problem. But let's get back now to this question of efficiency. We have a nice algorithm. What can we say about exactly how we implement it and what its running time is going to be? So here's where we go from a graph problem to a data structure. Here's a restatement of this algorithm focusing on what we're doing to the labeled set. So the main loop, we're repeating until the labeled set is empty. We're deleting from this set some vertex with minimum distance. I'll call that a delete min operation, sometimes called an extract min operation. Having deleted this vertex, we scan it. For each outgoing arc, we look at the cost, the known cost of V plus the length of this arc, and we see if we need to do an update or not. And there are two possibilities. If W is unlabeled, we may have discovered a path to it, or we have discovered a path to it. We just want to give it its initial finite distance and add it to the labeled set. This is an insert operation into the labeled set. The other thing that can happen is if we found a better path to vertex W. So W is already in the labeled set, but we need to decrease its distance because we found another path. I'm going to call this a decrease key operation. We'll think of the distance, the current distance to the vertex, as being a key. What we're doing now is maintaining this set L, where every element in it has some key, and we want to know something about the sorted order of the elements in L with respect to the keys. We need to be able to do insertions. We need to be able to delete the minimum, and we need to be able to decrease the key of a vertex that's already in this set L. So those are the three operations, and the whole algorithm just repeats these operations. In particular, it's going to do one insertion at most for each vertex, one delete min for each vertex, and one decrease key potentially for every edge or many edges. And we can draw some conclusions about the running time of this algorithm. On a graph that has n vertices and m arcs, the algorithm takes linear time in the number of vertices and arcs plus the time for the data structure operations, which are at most n inserts, at most n delete mins, and at most m decrease keys. We need a data structure that efficiently supports these three operations on an initially empty set of vertices, each of which has a real valued key. This kind of data structure is called I like to call this a heap. Knuth called it a priority queue. Take your pick. So now we've reduced our problem to implementing a heap. And this is a classic data structure problem. Dijkstra, in fact, in his original paper on this problem, used a number the vertices from 1 to n, let us say, have an array that's indexed by vertex number, and in the array position, you've got the current key stored. So every time you want to do an insert, that's just a matter of putting the new key in there, or a decrease key, just change the key constant time. But to do the delete minimum, you have to scan the entire array. So delete min is the expensive operation. It takes linear time in the number of vertices. You have to do that n times. That gives you the bound that Dijkstra claimed, which is order n squared, where n is the number of vertices, which is in fact optimum if you have a graph that's extremely dense, where most of the possible edges are present. But of course, in practice, think of a road network, most possible roads are not there. The number of edges is more like proportional to the number of vertices rather than quadratic in the number of vertices. So it's only on dense graphs that this bound is best possible, and if the graph is sparse, one can do better. Williams in 1964 proposed an algorithm that significantly improves the time for delete min. I should say at this point that with a priority queue or a heap, you can sort n numbers just by inserting them, each one once, and then deleting the min and repeating that n times. We know that if you want to sort n numbers by binary comparisons, it takes n log n comparisons to do the sorting. If we're using binary comparisons to solve the problem, which is what we're going to do here, one of these operations, or possibly several of them, have to take log n time. We can't do everything in constant time. This is one of the few instances for relatively simple problems where we can actually prove a non-trivial lower bound. We cannot solve this problem. We cannot sort in linear time using binary decisions or binary comparisons. And that comes into play here. So our goal actually is to reduce for most operations to constant, and some operation is going to be log n because that's the lower bound. In any case, Williams invented this beautiful representation of a complete binary tree in an array with heap order on the vertices, and we'll get to heap order later. In his implementation, the time for each operation is log n. So insert, decrease key, and delete min all take log n time. So the running time for Dijkstra's algorithm then is a number of edges, because the decrease key operations, most of the operations are decrease key operations in general. Each one takes log n time, as do the insertions and the delete mins. And indeed, from a practical point of view, to date, the best algorithm in practice is some version of Williams' data structure. So he used a binary tree, but if you use a degree 4, a quadrary tree, you save a constant factor, and it works extremely well in practice, and this is the implementation of choice. But it's still not the best possible theoretically. So I got interested in this problem in the mid-1980s with a colleague of mine, Mike Fredman, and we observed that the decrease key operation is the one that happens most often. If you could reduce the time for the decrease key operation, you could get an improved running time. So our goal was to get decrease key down to constant. And only the delete mins have the log n time bound. And if we could do that, we could improve the running time of Dijkstra's algorithm on graphs with moderate sparsity. So we managed to do that. We invented something called a Fibonacci heap, which I won't describe. But it has the nice property that insertions and decrease key take constant time. Delete min is the only log time operation. And it's important to note here that with data structures, we're doing a sequence of operations. We don't care about each individual operation in isolation. We only care about the totality of the entire sequence of operations. So we're individual operations to be abnormally expensive, provided that there's some compensation that some other operations, either early or later, we introduced this notion of amortization, which considers algorithms that have this phenomenon where some operation key is constant and the time for delete min is log n when you sum over the entire sequence. So that gives us a bound of m plus n log n for Dijkstra's algorithm, which is better than this m log n time bound, assuming that m is sufficiently large but not too large. That is, you get the nonlinearity here, you get the log factor, but it's only times the number of vertices instead of the times the number of edges. Now, is this optimal? Well, in the worst case, yes, because you have to look at all the arcs, otherwise you might miss a shortest path. And there's a sorting problem embedded in here. If you think just of a trivial problem where I have one vertex and a whole bunch of edges, and I'm asking to solve this distance order problem, where I want to produce the vertices in order of their distance from the source, that's just sorting. So I got to spend n log n by the sorting lower bound. So this bound that we had on the previous slide, this is best possible subject to those constraints. But we can look at this problem more carefully. This is the worst case. There's a particular somewhat uninteresting graph that demonstrates that we've got a sorting problem here, but what about a real graph, like a road network or something? Can we take advantage of the graph structure? What if the graph structure is known in advance and the algorithm can be customized to take advantage of this? For example, with a road network, if you're interested in travel time is non-constant. Rush hour is certain roads are much more congested, right? So travel time goes way up. But the road network changes only very slowly over time. So could we design a shortest path algorithm for a road network, say, that would be customized for that network and that would compute shortest paths for that network, but not knowing the arc lengths ahead of time? So we could dynamically adjust the arc lengths and have the algorithm still do best possible. That's what we want to ask here. So my co-author's somewhat highfalutin term for this is universal optimality. But what we really mean is there an algorithm, a general purpose algorithm, that on any particular graph is going to minimize the running time and the number of comparisons to within constant factors on every graph as compared to the optimal customized algorithm for the given graph. So I give you the graph, but I don't give you the arc lengths. You can design your own favorite specific algorithm for that graph. I'm going to give you a general purpose algorithm that I'll tell you here in a minute. And I claim that it's going to be as efficient as your customized algorithm on that particular graph and on every other graph as well. That is, for the distance order problem, the answer to this question is yes. And indeed, essentially, Dijkstra's algorithm, sufficiently modified, gives us the positive answer. So we need to change the algorithm in an interesting way. But more importantly, we need a new heap implementation to get this universal optimality. So we have to go beyond log n per delete min. Somehow this algorithm has to be adaptive to the details of how it's path here, and single all of these vertices sitting off to the side. So let's suppose there are k vertices here, right? So without doing any comparisons, because there's only a unique way to get to each one of these vertices, in arc lengths. And then if I run a merge algorithm, I can get the total sorted order of all the vertices. Depending upon what the lengths of these edges are, they're going to get interspersed in here when we compute a final distance order, right? So the time to, that's a customized algorithm for this particular graph. The time to do this computation is linear in the graph size, plus I got to do the sorting of these guys. That's k log k, because there are k of them. Plus I have to do this merge step, which is linear in the graph size. So k log k plus n is possible here. But if you run the Fibonacci heap or any other version of Dijkstra's algorithm with a standard heap, the first thing that is going to happen is it's going to scan the start vertex, and then it's going to put all k vertices plus this one into the heap. And then if it happens that all of these, let's suppose this entire path has length shorter than all of these individual edges, then what is going to happen is that one of these is going to get deleted from the heap, and then the next one is going to go in, and then you do another delete min, and that one goes out, and the next one goes in, and so on. Each delete min is going to take log k time, because there are going to be k, or actually k plus 1 vertices in the heap. So that's essentially n log k, but I said it's possible to solve this problem in n plus k log k. So m is equal to n roughly. M is the number of arcs, right? So Dijkstra with the Fibonacci heap is not universally optimal, because on this particular example, we can do better. So we have to change things somehow. The question is there a universally optimal algorithm? Good. Well, here's an observation. On this example, Dijkstra's algorithm inserts the vertices on the long path into the heap after the k vertices with the single arcs from S. Right? So we scan this vertex. We put all of these vertices plus this one into the heap. But the next one goes into the heap after all of these. And then the next one goes in after all of these. So there's some kind of order of insertion into the heap that's playing a role here. And maybe we can take advantage of this insertion order to do something more customized to this particular graph. Okay. So again, we need to improve our heap data structure to take advantage of some structure in the problem that's not captured by the worst. It turns out to be the right property. It's something called the working set bound. So we put an item into the heap. We consider the time when it's in the heap. So it was inserted at some time. It lives in the heap for a while, and then it's the minimum and it gets deleted. We count the number of items that are inserted into the heap after X. This item X is inserted, but before X is deleted. That's the working set of X. This does not count things that were inserted into the heap. Insertion and decrease key take constant time, but a delete min takes log of the working set size time. That is, we can ignore items that were inserted before this particular item is deleted. This seems like a rather bizarre notion, but it turns out to be exactly the right notion. It's the notion that gives us a solution to this question. So with this idea, we can ask two questions. Is Dijkstra's algorithm using a heap with the working set bound, which turns out to be better than the worst case log n per delete min? Is this universally optimal? That is, does it give us the best possible algorithm for any graph? And second of all, is there a heap with that has the working set bound? Can we do an implementation this efficient? Fortunately for us, the answer to both questions turned out to be yes. One without gets us no place. So there's a theorem that on any graph, if you run Dijkstra's algorithm using a heap with the working set bound, it's universally optimal in running time. And it's within an additive linear term of being universally optimum in comparison. Now we're counting comparisons of sums of arc lengths. That's our measure of efficiency here. And I'll come back to this additive linear term if I have time, which I'm rapidly running out of. I'm not going to go into the proof. Let me just again say that this is the theorem we want, except for this interesting linear term in comparisons. Not so important, but we can get rid of it, and we can get rid of it in an interesting way, as I'll show eventually, I hope. So that's good. So the working set bound would give us some result here, except we need a data structure that has the required efficiency. But before I go into that, let me just mention at a very high level how this works, because my co-authors started out with a rather ad hoc proof. We have to tie the working set bound to somehow the behavior of the algorithm. So what's the lower bound here? We're given a fixed graph. There's some kind of set of possibilities of distance order depending upon the choice of arc lengths. So we'll say a search order is a total order of the vertices such that S is ordered first, and there has to be, if you have a vertex that's not S, there's some arc from a smaller vertex in the order to that vertex. That is, there's some kind of spanning tree from the start vertex out to everything else. It's essentially counting the number of different shortest path trees that possibly exist. Now, more or less what happens here is that search orders are in one-to-one correspondence to the possible outcomes produced by Dijkstra's algorithm, and the search order is uniquely determined by the arc lengths, provided that you have a consistent tie-breaking rule. So if you're using binary decisions to identify the correct search order, however many possibilities there are, the number of comparisons you have to make to solve the problem is log of the number of search orders. This is just like the sorting lower bound. The n log n sorting lower bound is the same idea applied to this particular problem. So if we define D to be the number of possible distance order problem, that gives us a lower bound target, and we can then tie this to the sum of the delete min times if we have a working set bound heap. So we can prove that the sum of the logs of the working set sizes of the elements X in the run of Dijkstra's algorithm on this particular, and the proof uses a beautiful lemma that comes out of earlier work on a related problem that I talked about Saturday in TAR2 that I'll mention at the end. Nice technical stuff, but let's not dwell on the technicalities here. All right. Second part, is there a heap with the working set bound? Well, it turns out this is a question that John Iacono asked in the year 2000. I did some work on binary search trees, which is a different kind of data structure. and also on various sorts of self-adjusting data structures, including something we call a pairing heap, which is a self-adjusting heap structure. And I might even have, no, I don't have slides on that. Iacono proved that this data structure has the working set bound if there are no decreased key operations. And he proved this bound without having any application whatsoever. So 25 years later, 24 years later, we discovered this application of this concept that he was playing with from a theoretical point of view. There's another kind of variant of this data structure that removes the heap ends empty property. So the point is there are data structures that look like they have the working set bound that already exist, and there are others, but none of them supports the decreased key operation. And we want the decreased key operation to be constant time. So we had to design our own new heap implementation to make the decreased key operations constant time. And I'll describe that a bit at a high level. So this is a new heap implementation that has the working set bound, constant time for insertion, constant time for decreased key, log of the working set size for a delete min operation. We built our data structure from Fibonacci heaps, which do have constant time per decreased key, but we don't use a single Fibonacci heap. We use a sequence of Fibonacci heaps because somehow we have to keep track of the insertion time order. We're favoring elements that are inserted more recently. If I'm inserted more recently and other people are inserted earlier, they should not affect my removal time. So we'll represent our one outer heap by a list of inner heaps. This list is ordered by insertion time. Well, let's look at the picture here. Here's the picture. So there's a sequence of, each one of these is a Fibonacci heap. There's a little one in the front, then a bigger one, much bigger one, much bigger one. This is the old stuff. This is the not so old stuff. This is the less old stuff. This is the new stuff. When I insert a new item, it goes in the first one. So these are roughly ordered by insertion time, but they're not totally ordered by insertion time. Everybody in here was inserted after everybody in here, which was inserted after everybody in here, and so on. The sizes of these things, the first one is constant size. We can make the size of the next one the square. That's good. So we end up with a relatively small number of these things, like double logarithmic. And this is basically the data structure. List of Fibonacci heaps. We can't let the small one grow too big. When the small one grows too big, we have to merge it into the next one over. And if that one gets too big, we have to merge it into the next one over, and so on. There are a lot of technical details, but we worked out all the technical details to get this to work. And I think I will skip some of the technical details here in the interest of time. This data structure was specifically invented to have this working set property. It is not what I would call one of these simple data structures that I love to see. So I think it's an interesting question whether there's the right data structure. This is not the right data structure for the problem, I think. It has some nice characteristics, but there's more to be done here. Let me turn now to this question of universal and number of comparisons. Let's go back to this interesting example where we have this long path. This path, we don't need any comparisons. We can just run along here and add up the arc lengths, and we get the length of the shortest paths to all these vertices. And furthermore, we get them in sorted order in this list. This is kind of the bad case. This additive linear term is significant if the number of possible outcomes is small compared to We want log of d to be small, much smaller than n. Then we have to worry about this linear term. But there's a nice way to avoid this problem, which I'd like to describe now. There are various ways to do it, but here's a simple one. We can take advantage of a well-known technique in graph algorithms, which is to break the problem into smaller pieces. So how are we going to break it into smaller pieces? If I start out from a vertex S and I'm going off to somewhere and there's some intermediate point, and to get to all the far points, I have to go through the intermediate point, then I could start a new shortest path computation from there once I get to that point and continue. And that's going to be the idea. So these points that I have to go through, I'm going to call them bottlenecks. And here's the definition of a bottleneck. It doesn't capture all the points that have this property that to get to the other side, I have to go through them, but it captures enough of them that I get some benefit. So if I do a breadth first search, ignoring arc lengths, I just go one step at a time, starting from the start vertex. I do 1 hop, 2 hops, 3 hops, and 4 hops, and so on. I get the hop length for each vertex. It's unique in its level. I'm guaranteed that to get to the other side, I have to go through it. So I just do a breadth first search, which takes linear time. I find the vertices that are unique in their level. Those are the bottleneck vertices. I do that in a pre-processing step. And now, here's a trick question. What are the bottlenecks? See if we're paying attention. I'll let you ponder this, and if I come in, here's what we do with the bottlenecks. I'll call this recursive Dijkstra. We find the bottlenecks in this pre-processing step. Then we begin Dijkstra's algorithm starting from our start vertex. If then we get to another farther bottleneck, we suspend and restart and so on and so forth. We start building our labeled set and so on. We've got some kind of heap we're maintaining. We find the distance to this first bottleneck, V1. We suspend this Dijkstra computation. We restart from V1 with a new heap. V1 has its own heap. Each of the bottlenecks gets its own heap. So there's this secondary advantage, which is that if you have this graph with this partitioned structure, the heap sizes get smaller. And I mean, you break up the heap from one big heap into a bunch of small heaps. So while we're running the V1 Dijkstra, we find another bottleneck, V2. We suspend V2's computation, V3. We finish V3, we back up. We finish V2, we back up. We finish V1, and we back up. If we get an arc that goes, we cannot have any arcs that go forward in this picture that jump past the bottlenecks. That's the definition of bottlenecks. But we can have arcs that go backward, and these would cause decreased key operations in these heaps and these suspended computations. That's okay. We just do the appropriate updates. No problem. When we get done with this entire computation, we will have computed within each of these a shortest path length. And if we add the paths to the appropriate bottlenecks, we get the distances to all the vertices. But if we want them in sorted order, we have to do one additional step, which is we have to do some kind of merge process. And again, I'm going to omit the details, but there's another data structure that allows us to do this efficiently. It's called a finger search tree. We put this all together, and we got linear overhead, and the total time for all the Dijkstra computation is proportional to the number of comparisons, and there's no additive end time anymore. On top of which, this idea seems maybe interesting anyway. All right, so to summarize, recursive Dijkstra implemented in using a heap with the working set bound does what we wanted. It's universally optimal. There's another alternative algorithm that actually does scan the vertices in distance order, but it's as opposed to recursive Dijkstra, but it's maybe not as elegant, so I presented the one and not the other. Here's the paper. There's a version on arXiv that I'll refer you to. This is work that we did in Fox 2024. This is a basic problem. It's a new way of looking at a basic problem. Again, I suggest that in spite of the fact that there are a lot of algorithms and data structures in textbooks, but we don't understand everything. And there are even fundamental questions that I'm sure can be answered that we have not yet answered. So there's a different answer to the Dijkstra question. What I showed here is that Dijkstra's algorithm, modified in the way I described, is optimal if we want the order of the distance, if we want the vertices in order by distance. That is, if we turn this into a sorting problem. But in practice, maybe you don't care about the order. Maybe all you want is the distances. Now it's not a sorting problem anymore, and it's maybe the right problem, and the lower bound doesn't apply. And in fact, you can do better. If all you want to do is compute the distances, but not the order of the vertices by distance, there is in fact an algorithm that runs in m times log to the 2/3 of n. This is faster than Dijkstra's algorithm, asymptotically faster than the Fibonacci heap implementation. Quite a bit more complicated, but it demonstrates that here's a different way of looking at the problem, and you can get a different answer in this case. Here's the reference. Again, this is very recent work. So one wonders, can we in fact compute shortest distances in linear time? It's not out of the question. This bound looks too bizarre to be best possible. There's another interesting open problem. Just one more word here. What I talked about in Tart 2 is a related problem, which is sorting using partial information, which is a pure sorting problem. After we discovered this Dijkstra algorithm, John Iacono, who's done a lot of work on data structures, observed that this idea of the working set property can be applied to this sorting problem. So the sorting problem is, normally when you're given a set of items to be sorted, you have no information. But suppose somebody tells you the outcomes of certain comparisons ahead of time. For example, I want to merge two sequences. So I know the total order within each sequence, but I want to merge. Or suppose I have several sorted sequences and I want to do a multi-way merge. Is there some sorting algorithm that takes maximal advantage of this initial partial information? Turns out this idea of a heap with a working set gives a simple solution to this problem that is universally optimal in the same sense that the modified Dijkstra algorithm is. And here we don't need to use, we don't need any decreased key operations. This is just inserts and delete mins. So these simple data structures like pairing heaps that have the working set property but don't support decreased key work and give us an optimal algorithm in this setting. And this paper will appear in Algorithmica, but it's also on arXiv, so I'll refer you to that one. So this is an example of something that John was aware of and we were not, a hidden connection between problems in somewhat different domains. And I think now I will stop and be happy to take any of your questions. Thank you.
Thank you very much. It's time for questions. You can ask about this particular topic, but you have a chance to ask maybe another questions regarding data structures and algorithms. Yes, please. Who would like to start?
Thank you, Professor Tarjan. I like your talks very much, and this was excellent. I wonder about graphs which are of very large size. For example, all the routes at the global level, like OpenStreetMap, which takes 1 terabyte of data. And obviously I won't be able to process that much data on my phone. So are there some ideas not to consider the whole graph, but only maybe some part, of maybe using this working set, maybe only neighboring vertices or edges? And also I know that post-quantum cryptography uses exponentially large graphs, which exceeds the number of atoms in the universe. Obviously, we are not able to store them in memory. So what are the solutions for such problems?
That's two questions. As far as short algorithms for road networks, definitely do not look at the entire road network. And I'm not sure how much is stored on your phone and how much is in the cloud, but they take advantage of hierarchy and also the fact that there's some directionality. So the phenomenon is that there's this hierarchy of road types, and generally what you end up, main road out to the highway, and then you take the highway for a long distance and do the other thing on the other side. So there are these structural properties, and you also know the general direction you want to go. So these algorithms run in significantly sublinear element concurrency. I think getting concurrent graph algorithms, there's been some work on this. It's very hard. You know, concurrency is very powerful, but it's most efficient in situations where the problem is embarrassingly parallel, which means there's not a lot of interaction between the processors, which is not necessarily true of.
Thank you for a very exciting talk. The question, what might be your opinion about shortest problem in graphs when we have also negative edges? So we are left with Bellman-Ford and very unpleasant running times. Do you think there are any hope ever to improve that, or this is kind of hard? You know, also probably not provable.
So the well-known algorithm there is Bellman-Ford, and it runs in vertices times edges time, and I think it's improvable, but I don't know how to do it. And there may even be results there by now. There's been amazing work in the last 10 or 15 years on network optimization problems like network flow, bipartite matching, multi-commodity flow, minimum cost flow, and so on. Getting almost linear time algorithms for some of these problems using very sophisticated techniques, rather complicated algorithms. What we need there is simplicity.
Any other question?
Okay, I have one more question. What if we want to find not just one path, but like two shortest paths, or three or several shortest paths? Are there some non-heuristic based algorithms?
So there are various versions of that problem. One is find the second shortest path, third shortest path problems. There are classic techniques, but you can also ask the question, give me a set of diverse paths, say vertex disjoint or edge disjoint, and then it becomes a min-cost flow problem. The answer is there are known techniques. I'd say there's probably more work to be done there. actually.
Actually, I mean, when I use some navigation software, I'd like to have not just one shortest path, but like 2 or 3. Maybe the second shortest path is better. It goes through a better road, maybe near the sea. So how to find this? It's maybe not a disjoint path, but the second shortest path.
Yes. I think this is a question for the engineers who work on these things. I think some of these routing systems will give you alternatives in certain settings, so they must be looking for alternative paths, but I don't know how they do it. I was working on this about 10 years ago when I was consulting for Microsoft, actually, but I kind of lost track of the recent stuff in the area.
Okay, next question.
If there would be any application for that, and if the implementation would...
Depends how you formulate it. If you allow, what do I want to say? If you do not allow repeated vertices, it's essentially the traveling salesman problem, which is a classic NP-complete problem. So you're at the level of heuristics and specialized techniques for the traveling salesman problem. From the worst case point of view, nothing is known that's better than exponential time. So that's kind of the short answer. If the graph doesn't have any cycles, if it's a DAG, then the shortest path problem is equivalent to the longest path problem. You just you change all the plus cost to negative and negative cost to positive, and shortest turns into longest. So in that case, the problems are equivalent, and otherwise longest paths are much harder to find than shortest paths, at least as far as anybody knows.
Okay, thank you.
Okay, next.
Thank you for your talk. So I'll have a simple terminology question, which my students ask me sometimes. It's about dense graphs and sparse graphs, because so much of these problems depend on the size of number of edges. And it seems there is no clear boundary. There is a dense graph and a sparse graph at some moment. So what would you tell students?
What would I tell students? All graphs are sparse. A set of dense graphs in practice is a set of measure 0, basically, if you're dealing with large problems.
Thank you.
Okay, who else? Okay, I also would like to ask one question. If we talk about some optimum, yes, we also said about some optimal solution data structure or something like that. Usually I ask what is optimum, how to measure it, because, for instance, you propose very, very good algorithm here. Some of these listeners, participants will go home, will implement, and then will say, no, this algorithm or data structure works slower, requires more memory, and so on. That means that probably one person has one opinion what is optimum, and another person has another one. What is optimum in your case?
This is a theoretical result. As I said somewhere in this talk, the state of the art for practice is you use a simple heap, which is just an array-based heap. You run Dijkstra using that, and that's by far the best solution, rather than some more complicated data structure. So we're working in the theoretical world here. I like to devise simple algorithms, and some of them have in fact been used in practice. I'm very proud of that fact, but it's a challenge. I think you always have to do experiments, and then you have to be suspicious of the experimental results, because it's very easy to see what you want to see when you're doing experiments, I think. But yes, simple is better. Try the simplest possible solution and see if that's good enough, and if so, you're done. It's only if you're dealing with very large problems and the simple ideas don't work that maybe you want to think about more complicated implementations. I would also say that, yeah, it's not the algorithms that are the sources of inefficiency necessarily, but in modern computer systems, you get layers and layers of abstraction in the software, and this slows things down by huge constant factors. So start writing in lower level programming languages if you want efficiency. You don't necessarily need to change the data structure. I think there is too little appreciation for how much we lose through these beautiful layers of abstraction. I mean, computers are really fast, but if you're dealing with huge problems and you really need speed, you would better maybe strip out some of the layers of abstraction. This is the old school me speaking. The first computer I programmed on was the Bendix G15. It was refrigerator sized. It had 2,000 words of memory on a rotating disk. The input was punch tape. We wrote programs to flash the lights on the front of the screen. There, you really had to worry about both space and time. So you're lucky that you have access to these incredibly fast computers with vast memories. The world has changed a lot in computer technology. You have no idea, I think.
Okay, thank you. I would like to touch another topic we discussed a little bit yesterday in Tartu. You have huge experience in data structures and algorithms, and yesterday I asked what to answer to my students if they say that artificial intelligence can make this low-level programming very well, better than we can do, and maybe we don't need to learn data structures, learn some basic algorithms. What is your opinion?
As a teacher of data structures, I hope that's not the answer. I think the stuff is a beautiful intellectual challenge, and I think if you're going to be a professional, you had better know how some of these things work. And these large language models and so on are amazing, and they're going to get better, but they also hallucinate. And if you're going to use them to do programming, you had better trust but verify. So I think software verification, especially when computers are writing a lot of the code, is extremely important. And I also think people are probably still better at coming up with the ideas. Maybe the computers are better at doing the actual implementation. So use them for what they're good for. And maybe they can suggest ideas to you, but I still think people are more creative than artificial intelligence is.
Okay. Thank you. Questions? Maybe more? Oh, I see.
Wolf is going to embarrass me now. He's got his list.
So, I would like also give some opportunity for the person who are on the last row. I will show that I can run.
Yes, so thank you very much for the lecture. And I have the question specifically regarding to A-star algorithm. So if you consider that adding the heuristics to the Dijkstra's algorithm, the A-star algorithm, it selects the specific direction to the smallest pass of via the graph. And why do people still use Dijkstra if it covers scans all of the verticals around? If we can just use heuristics and go into the specific direction, and it will be more optimized in that case, maybe.
Absolutely. So the A-star algorithm, you can think of it as a hyped up version of Dijkstra's algorithm where it's given some estimate to the destination. And then you can combine the estimate with the actual distance to the given point. And you've got a heap where you're using that as the criterion. And the better the estimate is, the more focused the search will be. That's a very powerful idea. It relies on having a good distance estimate. So in road networks, this is one thing that one can use, in fact, because there is some directionality, and that's one way to get this isolation. So you get this serious sublinear performance. It's very important, but it requires that you have a good distance estimate. Otherwise, you can't use it. I try to present this in my class, actually. It's kind of the next step beyond Dijkstra. You can also think of running this bidirectionally, which is another important idea. So there are a lot of additional ideas in shortest path algorithms, and this is only kind of one of the basic ones.
I saw that one person more wants to ask some question, and it looks like the time to end our question and answer sessions. And before I give microphone to this person, I would introduce you with this person. Today's lecture has been made possible thanks to the our supporter of Wolf Hader. He is at this moment a bronze level patron of the University of Latvia Foundation, and he has supported quite many events, activities in our university, and I hope he will support us in the future as well. And he has also maybe some question.
Minimum spanning tree is another one of my favorites, long-standing. How do I choose problems? I go to conferences, I read papers, I talk to people. I get problems from talking to people and seeing what resonates. I think collaboration, one of the beauties of this field is that people love to collaborate with each other. It's a very human activity, even though what we're doing is quite abstract. So you get satisfaction out of working with people, and you also get great ideas. So find people who are smarter than you are and see what they're interested in. And
yeah, you wanted to embarrass me too, yeah? Yeah, thank you once again for everything, Robert. And I think, yeah, it's pretty late. I think we have to finish now.
Thank you all.
I would like to thank you